The volume of an ideal gas varies directly with the temperature T and inversely with the pressure P. If a cylinder contains oxygen at a temperature of 300 Kelvin and a pressure of 15 atmospheres in a volume of 100 liters, what is the constant of proportionality, K? If a piston is lowered into the cylinder, decreasing the volume occupied by the gas to 80 liters and raising the temperature to 310 Kelvin, what is the gas pressure? This is a variation application problem because the volume V is going to vary directly with T and inversely with the pressure P. So volume V is related to these two variables. Since the volume is related directly with T, but inversely with P, that means that we're going to have a fraction where the variable T that we vary directly with is going to go in the top of the fraction, and the variable P with the inverse relationship is going to go in the bottom of the fraction. So T is going to go in the top, P is going to go into the bottom, and the constant of proportionality, K, is always going to be located in the top of the fraction. So K is a multiplier here in the top. So what we have here, we'll refer to it as the template variation equation. It describes the basic relationship between V, T, and P. But the first thing that we need to do is to use the initial conditions to find the value of K, which means that we need to go back up into the problem and find the initial conditions that can be used, which are here. It says that a cylinder contains oxygen and we're given the temperature of 300 Kelvin and the corresponding pressure and volume for that temperature. So we're going to plug 300 in for the temperature, 15 in for the pressure, and 100 in for the volume. And when we do that, we'll be able to then solve for K. So 100 gets plugged in for the volume, K is what we're trying to solve for, 300 is plugged in for the temperature, and 15 is plugged in for the pressure. So to solve for K here, the first thing that I'm going to do is multiply both sides by 15 over 1, which is the least common denominator of all the fractions in the equation. So 15 multiplied by the 100 on the far left is going to be 1500. And then 15 multiplied by this fraction over here on the right, the 15s cancel out and we're left with only 300K. So now to solve for K, we just divide both sides by 300 to get that K is equal to 5. So now we'll use this K value of 5, we'll plug it back into the original template equation, and we'll update the variation equation with this found value of K. So plugging 5 in for K, we now get an updated variation equation that is going to be 5 times T in the top of the fraction all over P. And then the last thing that we're going to do is we're going to use the updated variation equation in order to answer any remaining questions. So let's go back up here to the problem and notice that we've already found that constant of proportionality, K. K was 5. So the remaining question that needs to be answered is to find the gas pressure if the volume is decreased to 80 liters and the temperature is increased to 310 Kelvin. So we'll plug 80 in for the volume and 310 in for the temperature and then solve for P using again this updated variation equation. So we plug 80 in for the volume. We already found our constant of proportionality to be 5. We'll plug 310 in for the temperature, and we're now tasked with finding the value of P. So to solve for P, let's first multiply 5 times 310 to get 1550 in the numerator of the fraction. So I'll slide everything up just a bit to give us a little more space. And this time, instead of multiplying both sides by the LCD, because I have a single fraction on the left and a single fraction on the right, I'm going to instead choose to cross multiply. Cross multiply only works if I have a fraction equal to a fraction. It doesn't always work, so I usually will multiply both sides by the LCD, which does always work. But in this case, we'll multiply 80 times P, which will then be equal to 1550 times 1, which will just be 1550. Again, cross multiply is only allowed when we have a single fraction on the left and a single fraction on the right. So now to solve for P, we'll divide both sides by 80. So the 80s cancel on the left, and we get that P is equal to 19.375. And to determine the units, we need to figure out what the units were in the initial conditions for the pressure. So coming back up into the problem, we see that the pressure was measured with the units of atmospheres. And so we have to use the same units to measure the pressure in our question.